Good morning, everyone. First of all, I really just want to just acknowledge and thank the organisers of this for the opportunity to share my ideas and my thoughts on this. What I hope and believe is truly a revolutionary opportunity for healthcare and medical research in this country. Well, where to start? I hope everyone's had coffee. I have. I've got a lot of slides and I've got loads of stuff that I'm gonna race through, and I think I hope it's going to be as exciting for you guys as it is for me. So here goes. So the human genome, and I think first of all we really need to have a bit of an idea in our heads about what is the genome and what is this thing that we're talking about. You may remember this from your biology textbooks when you were in 10th grade or something like that. This is our 46 chromosomes that contain the 6 billion characters of DNA. So DNA is composed of these 4 different types of characters: A's, T's, C's, and G's that you may have heard from time to time. But there are 6 billion of these characters. We inherit 23 chromosomes from our mum, 23 from our dad. That's what defines the human genome. Now, the reason that this information is so extraordinary and valuable to us, and it's part of every cell in our body, and it's also the core piece of information that, from an embryo, from when we're a single cell, from that moment onwards, all of the information that's in our genome is what's used to inform the entire development of our bodies, all the way through as a fetus and as a baby and as we grow up, which is actually a pretty amazing thing to think about when you think of the sophistication of the human body, and you think of the extraordinary amount of information that must be in there for your spine and your organs, your eyes, your heart, every muscle in your body, all carefully and intricately designed or defined by the genome. And when you look at an identical twin, and this kind of tells you just how amazingly deterministic the information is that's actually encoded away in the genome, is that even the most subtle things like the way that your body tans, or the way that particular effects, the way that your hair recedes, and all the way through to disease and how you respond to different sorts of diseases is all ultimately encoded inside our genomes. So, and it's also the same information that defines not only the variation between you and the person sitting next to you, just out of, you might be interested to know that you and the person sitting next to you differ by maybe 4 million or so of these characters. Of those 6 billion, maybe 4 million are different between two people. But it's also the same information that, when it goes wrong, can lead to a huge number of different diseases. And in fact, almost every disease, whether they're genetic and inherited diseases or diseases like cancer, are ultimately either caused by or influenced or responsive to some sort of a genetic condition. So there's an awful lot we can learn about this. Why is this moving so quickly, and why is this such a phenomenal time in our history? So when we think about it, it's all gone really, really fast. It was just the 1850s or so that we even had the most basic idea of what DNA was and what even heredity was. So those early principles defined by Mendel and his pea plants just 150 years ago, and it was just 50 years ago that we worked out what this molecule was, DNA, and what shape it had through the discovery of the double helix. And our capacity to actually sequence this information, actually determine the order of those characters in the genome, was only possible in the 1980s on a very, very small scale, where we could sequence perhaps hundreds or thousands of nucleotides. Now, through this incredible revolution in technology, we're now able to which has really only been the last 5 or 6 years, that we've been able to sequence at scale and be able to accurately determine this information at speed. So I put this slide up. It's a slide from the McKinsey Institute that makes an interesting point, I think, that around the impact that genomics is anticipated to have in the near future. And you can see here these list of things like mobile internet, Internet of Things, the cloud, advanced robotics. These are really, really big technologies that are transforming that are transforming everything and have, trillion-dollar impacts. But you can see there, number 7 at Next Generation Genomics, with an anticipated financial impact, economic impact in the order of 0.7 to 1.6 trillion dollars. And if we scale that down to that's worldwide, but even to Australia, that's worth somewhere in the order of the pound for pound, in the order of about $26 billion to the economy of Australia. So this is a really big area. But why is this so? This makes it very different to any other type of test or a lot of other technologies, and particularly in healthcare. Why are these impacts as tremendous as they are? Is really what I want to talk about next. So you can see that across the world, the investments in genomics are huge and growing at amazing scale. So even within Australia, we were very fortunate through the vision of the New South Wales Health government to have a $25 million investment, which was the first of its kind in Australia, to really back genomics. The Melburnians, the Victorians followed suit a year later, and a year after that the Queenslanders caught up as well. But it was really great that we were certainly at the front of the pack here. But if we look internationally or globally, you can see that the investments in genomics are absolutely tremendous, and figures the US Precision Medicine Initiative in the order of $10 billion. The Chinese are also spending in the order of $10 billion. The French are now committed somewhere around 700 million euros, and the English as well in the order of 300 million pounds. So this is a really, really big industry that the world is racing through at the moment. But where is this excitement coming from, and what's sort of stimulating all of this is really the amazing amount of potential that it has in transforming healthcare. So these are the 3 areas that we really see this making a big difference in the near future. So, and first and foremost, and that's the one I'll talk about probably the most, is the capacity to diagnose rare and inherited disease in a way that's simply never been possible, and where the technology simply hasn't been there to achieve this in the manner that it is today. Cancer, cancer is ultimately a genetic disease, and the capability to sequence a tumour and provide an exact molecular description that tells you what is the actual cause of the cancer. It's not, which tissue it's in or which part of the body it's in. It tells you exactly what the biochemical basis of it is, which is therefore, provides your opportunity to target a very specific therapy to that cancer. That's really there. But the really big opportunity, and I think the one that's going to be most transformational, is how it will move from not just diagnosing disease and informing treatment, but really turning it around and looking at the capability to anticipate disease and to be able to stratify populations so that we can understand who is most susceptible to what, how they can change their lifestyles, and actually start to prevent disease rather than just treat it. So our vision at the Kinghorn Centre for Clinical Genomics around is really to not see genomics simply as a diagnostic product, but to actually to look at its impacts across whole of life care. So this really makes it very different to any other test that's existed in the health system, because what we're saying is that you can sequence a genome just once, make it part of your health record, and it can be read again and again and again in all of these different scenarios and conditions, whether that's planning to have a child or all the way through to diagnosing a disease or working out how your body responds to different sorts of drugs. And ultimately, at the grim end of this, even understanding why it is that somebody passed away. So what's made this possible is really this phenomenal change in the technology, which I don't have time today to describe in detail, but it is fascinating. So just 10 years ago, there was a previous sort of a technology that was used for sequencing, and it cost in the order of $100 million to sequence a genome just 10 years ago. And the first human genome cost in the order of $3 billion to sequence. So it was the advent of next generation sequencing in 2007 that really precipitated this phenomenal decline in the ability to read DNA. And in fact, by now, and we sort of reached this phenomenal milestone where, it's a reagent cost, but where if you have the instrumentation and capability, you can sequence a genome for about $1,000, which is a phenomenal hyper-exponential drop in price of a technology, which is really what's caused this very fast change. We were very fortunate at the Garvan Institute through a very generous philanthropic donation to be able to purchase the instrumentation to do this. It's called the Illumina HiSeq X10, which is kind of cool. It's got a great name, and it's has a capability of sequencing 18,000 whole human genomes per year. Now, what's really cool about the test, and I guess what the other thing is transformative about this, is that it replaces pretty much every other genetic test that's been used to diagnose disease. So if we think about that, there are a whole number of different things that are existing now in pathology that are used for testing, and whole genome sequencing basically covers the whole lot of them in one go, and does in fact replace thousands of individual tests in a single test. So we were one of the first 3 sites in the world in Australia, together with the Broad Institute and in Macrogid in South Korea, to really take the plunge on this. It's a fairly rare day that we go head to head with the big guys in Boston, but this was an opportunity to do that. So that's been I think defining for Australia and for the state. So the institute that I head really had the goal to bring genomic information into healthcare, and that's really what we were set up to do, and that was our mission to achieve. As I said, this has been fueled by around about $50 million now in both state government funding and philanthropic funding to achieve. This is not the kind of thing that where the competitive grant system does us much good, and it really requires visionaries to be able to bring this type of technology to life. So this is just a snapshot really of the evolution of our centre over the past 4 years, and I think really the only thing, there's a lot of people and they get smaller and smaller as they go to the right, because it turned out it took about 50 or 60 people to run the centre in the way that it is today. But the main thing I really want to point out on this slide is the fact that we're working now together with a remarkably multidisciplinary team of clinicians and bioinformaticians and scientists all together. So it's really drawn together a remarkable number of different skills and expertise, and people that ordinarily would never have spoken to each other. And of course now big data analytics is playing a big role in this. So when I set out to do this was kind of, I thought, well, right, what are we going to do? What's the point of my what we're trying to achieve? And it was really to be able to go right from, make this really simple. I want it so that a clinician can basically tick a box and say, I've got a patient, these are their characteristics, give me a genetic diagnosis, i.e. give me a report. Something that I don't want 6 billion characters of information. I want an interpretation of what my patient has and how I can better manage their care. It sounds simple, but in reality, of course, in between, there was an enormous number of steps that needed to be filled to achieve this. Both from the counselling point of view and to be able to responsibly put an individual, and subject an individual to a whole genome test, and they understand the implications of this, all the way through to the actual sequencing, the gathering of the data, bringing it all back together, and then interpreting it and returning it back to the patient. So, in a nutshell, this is sort of what we achieved, and this is a very fast slideshow or snapshot of what the last 4 years looked like for us. We needed to sort out specimen reception, which is a pretty basic sort of a thing, and we were able to build a collaboration with SIDPath at St Vincent's Hospital, who are next door to the Garvan Institute, to do that. So that was that ticked off. We needed high throughput whole genome sequencing. I won't say this is plug and play technology. When you're amongst the first 3 in the world to get a new tech, it doesn't quite go out of the box. But we certainly did manage to make that work, and it took a couple of years to really bring it up to scale. But we are now sequencing 1,200 genomes per month, and we have sequenced over 10,000 genomes through the centre to date, which is more genomes have been sequenced now in this country in the last 3 months than have been sequenced in the last decade. We had to be able to create an automated system, or as close to an automated system as we could, to be able to capture phenotypical information, which is essential in providing a diagnosis. We needed to be, at a clinical standard, so that this was actually robust enough to take to the clinic. We had a phenomenal amount of people basically saying, "I think you can't do this," and that this is a research tool and this is not fit for the clinic. That was a huge challenge, and it's not to say that it certainly wasn't easy, but we went through this systematically, and we actually ended up winning an award with our analytical pipeline, and showed that it was more accurate than any other technology that's been available to date to provide a genetic diagnosis. we needed a lot of clinical expertise, and a big part of this came through a partnership that we had with New South Wales Health Pathology. We absolutely couldn't have done this on our own, so that partnership was essential. And that clinical expertise has now led to the diagnoses of hundreds of cases of genetic disease, and we get we're very pleased to be able to say that we get a diagnostic rate of over 50%, which is well over triple of what was possible previously for rare and inherited disease. So this is a really an amazing technology. Of course, we needed quality systems. That was part of our accreditation, which is ultimately was the, sort of 3 years of work to be able to get a shiny certificate. This one was definitely harder than my PhD, I can tell you. So it was a really phenomenal amount of work done by a very large team of people. And at the end of this, of course, we needed to have an avenue to be able to deliver this as a clinical product, and that's what we did through a spin-out company that's wholly owned by the Garvan called Genome One. You can go to the Genome One website. It's actually the name of the company is also the URL. So you type genome.one into your browser, and you're there, and you can learn more about the company. So in the last few minutes, I'm just going to talk a bit about our focus today in Genome One, which is in the area of rare disease diagnostics. The reason we started out in this area was because, of course, rare disease is there was a very high clinical need, and the current approaches to diagnosis for rare disease and inherited disease have been largely extremely inefficient and challenging. So there's about 1% or so of Australians that are affected by a severe genetic disease. And this diagnosis can, of course, provide treatment, patient management, reproductive choices, and future certainty. So there's a lot of great advantages that go outside of a cure that are still very, very valuable to individuals with rare disease. And as I said, with diagnostic rates of over 50%. This didn't require a complete transformation of the health system. That's the other thing that made it attractive to us, because the numbers of individuals involved are not completely huge just yet. So it was certainly a tractable problem. But I'll talk about what I think needs to happen next for this. And the other thing I just wanted to mention was that the cost savings were so absolutely clear that the health economic studies that we are constantly pushed towards having to do, which we are now doing in practice. So you can see this as a table. Dora, you don't need to be able to read all of this, but where you can see here, these are 10 cases of individuals that have had rare disease and what the cost of the testing has been over the course. And in the middle column there is the number of weeks that they've been undiagnosed. So those figures there are in dollars. There's sort of $23,000 of unproductive testing over a course of 192 weeks. So you can see the list there of really what we were facing. If we zoom into a couple of these, this is what it looks like. This is what the testing, this is just the cost of the tests that has gone on to these individuals. So you can see there on the one on the left, $23,000 worth of tests that were all negative. On the right, $15,000 worth of tests that are all negatives, and this does not include the cost of the clinicians, the specialists, and all of the other time and lost time, of course, by the families as well, into trying to find a diagnosis. Each of these cases, we were able to diagnose with whole genome sequencing in a single test. Now, if that's not enough of an argument for why this technology really needs to be available as quickly as possible in the health system, is that the parallel argument around this is also the amazing value that comes from the research. So we see now that there's the capability that with each one of those tests that's actually negative, and we're certainly not perfect, 40-45% we don't diagnose, but that information is immediately valuable to medical research, so that one day those individuals can get a diagnosis, and that they have the knowledge that their medical information is actually being used to advance the science and to understand their disease. And I think that's a remarkable feature of whole genome sequencing, is that it has that opportunity for a real synergy between medical research and the clinic. But this is just the beginning, and I'll finish and leave you with these thoughts of where this technology is really going. We're starting with rare disease. We'll move quickly into areas, kidney disease and diagnoses of cardiovascular diseases. These all have a genetic basis. and we can make real progress on those. But as I said, there's a whole of life care solution effectively that can be proposed through whole genome sequencing that we intend to implement over the coming years, and we can see is really possible, feeding into areas like pharmacogenomics, understanding why it is that some people respond exceptionally to a drug, why some people respond poorly, and why others actually respond adversely. All of that information can be anticipated by the genome. So where we see this moving forwards from here is really the integration of all of the data from health records and from the environment to next actually better understand what the genome does. As it stands today, and this is an extraordinary figure, we can interpret just 1% of the human genome. There's 99% of it that we still don't understand. So the opportunities for understanding complex disease are wide open, and in anticipating new disease. And in fact, as you can see in that last picture there, the possibility to actually take the genome to start to understand, well, which part of the genome is it that makes your face look the way that it looks, that makes you age the way that you do, and makes you respond to different environments in the way that you do. So I think that's really where this technology is going in the future. We're seeing a very close combining, which is really being able to take phenotypical information in different ways, characteristics of individuals that are coming now longitudinally through mobile devices, and we're really seeing that that's where this is going in the future, and that this will ultimately inform a new generation of capability in terms of informing clinical decision making. So I want to leave you with these last few thoughts. That whole genome sequencing is a single test that can potentially diagnose any heritable disease and predict health outcomes. We do anticipate that it will ultimately become part of our health record. It's probably more of an if rather than a when. A when rather than an if. And as I said, the scientific challenge today is understanding more of the genome and understanding what it all does. And this opportunity that I see for genomics in closing the gap between medical research and the clinic, and how this will really drive the future of healthcare across the board, and that we really do see that precision medicine requires this genome-centric health system. And with that, I'll finish and acknowledge the amazing team of people that brought all of this together over the last few years. It's been an enormous effort, and just to acknowledge again the New South Wales Health and the OHMR, the Kinghorn Foundation, the NHMRC and the Garvan Foundation, and Bioplatforms Australia for contributing funding to make this possible. Thank you.
Thanks, Marcel. Open up your Slido and ask questions, and if anybody wants to ask also prepare to ask a question orally, just put up your hands and somebody will come to you. Marcel, have you had your genome done?
Yes, I have.
Anything you'd like to share with us?
Sure. Yeah, no, I've got a genome story. So I did have my genome sequenced a couple of years ago. I thought, if I'm going to try and
so is this just a blood test
to the world,
your body
just a straight blood test. And I actually learned that I had a potential adverse reaction to general anaesthetic. I've never had general anaesthetic, but it was something that I was certainly able to inform my doctor about as a potential adverse reaction to general anaesthetic, which is potentially life-saving, so who knows? Okay,
the anaesthetists in the audience are taking note. So the second question there is one that I was quite interested to ask. There's a risk for individuals in finding out things about their genome, and we do not have a Genetic Information Protection Act in Australia, which either jurisdictionally or federally. How much of a barrier is not having protection? Because you might find out things about yourself which have an impact on your family, which then they are obliged to declare to life insurance companies.
Yeah, that's right. So first of all, to make clear, health insurance, at least in Australia, is can't be discriminated by genetic information.
Life insurance can.
But life insurance certainly can, and as well as income insurance as well. So these do remain sensitivities in the case of the sequencing of well individuals and finding out that you may have something that causes a disease. That causes a problem. But in the case of an individual that has a disease, in any case, it really is it's obviously it's kind of a no-brainer, because you've got an opportunity to actually treat the disease in the first place. Our anticipation is that insurance will actually catch up with this, because what needs to happen, of course, is that insurance companies would actually benefit from having knowledge of that their patients have pathways to actually prevent disease. It's a win-win situation, in fact, if our population is healthier to reduce costs to the insurance system.
You're going to have to prove that to them for for the actuaries to understand it. This is not MBS listed, obviously. Who pays for this genome testing in New South Wales Health at the moment?
Yeah, so it varies at the moment from place to place, and this is certainly an issue. There are some hospitals have a genetic testing budget. It varies in size depending on how much genetics they do, and then in some cases the hospital has got the opportunity or capability to pay for it, but it's fairly restricted at this stage. Individuals can pay for it as well as privately.
You can turn up and ask for it, which is one of the other questions on Slido. You can just turn up and ask for it?
Well, the normal process today is that you would be referred to a clinical geneticist, most likely, or another medical specialist, and they would, if there was a genetic basis for the disease, they could then go ahead and audit the test. So an individual can't audit the test, it's a clinician audit test.
So you insist on being a referral having happened. You won't take people off the street.
What's that, sorry?
You won't take people off the street.
We don't directly. Genome One doesn't see people off the street, but you can go to a clinic. So actually just yesterday, and I should have mentioned this in my talk, I didn't have the picture in there, but St. Vincent's Hospital just opened a clinic called the Clinical Genomics Unit, and you can indeed just go up to there and see somebody to be referred for genomic testing.
Now, clinicians are notoriously bad at ordering tests. Notoriously bad. They probably haven't got a clue how to order genomic testing.
Yeah. So there's this
is called a career-ending question. You're laughing hysterically.
Without a shadow of a doubt, there is an enormous educational process that's needed to make this system work, and there is no question that's GPs, and that's all the way through to every medical specialist, because ultimately, as I've really been trying to articulate, genetics impacts on across every specialty. There is basically no medical condition or intervention by the health system that wouldn't benefit from some a priori knowledge of an individual's genome, whether that's an organ transplant or whether that's treating them with any drug. Ultimately, there's a genetic consequence that could inform healthcare.
So it's $1,000 for a high quality sequence. In other words, you're giving a high resolution sequence here with low error rates.
So $1,000. This
is where the sales process gets questioned.
Yeah, here we go. So the $1,000 buys you is what the cost is of the reagents to put inside the machines. So the real life cost of a delivered genome through the health system as a test that's been interpreted and where all the magic and bioinformatics has happened is about $4,000 at the moment.
Right, and that's a high quality detailed genome.
That is a very high quality genome that covers pretty much the whole thing and can diagnose any disease.
And the error rate?
So
in other words, you say you've got a rare disorder. What's your
the error rate is effectively close to zero because we sequence the genome 30 times. So there is an error rate, but the chance of getting the same error on the same position 30 times is far less likely than being struck by lightning 10 times on the same day.
So I trained in has happened. I think. Having trained in pediatrics, pediatricians just love the rare disorder. They just love it. It keeps them going, but very rare that you can do anything about it. So which is important for parents, I'm not decrying that, but so you've made a 50% diagnostic rate.
Yes.
Putting your hand on your heart, how much difference have you made to families and children, apart from the knowledge that they've got a name for what's wrong with their child?
So the information that we get back from families is that it's been absolutely invaluable to them. It stopped them having to interface with the health system again and again and again for a course of years. So putting an end to that is for them a really big deal. The second one, and this is where the urgency comes in, are individuals that want to have a second child or a subsequent child and have knowledge of what the risk is of having another child with the same rare disease. And I think that has been incredibly valuable to those individuals.
I know I'm taking up time here, but then in that situation, do they then have, for pre-implantation genetic diagnosis in an IVF program, which is what you're talking about, you have to go through another sequence like this, or can you go and target the gene?
So there's one of two things that can happen. We can either inform the individual that it was in a phenomenal bad luck, that is that the mutation happened in either at the point of either the at the point of conception. It's what they call a de novo mutation. That means that neither of the parents are actually carriers of the disease. The mutation actually happens spontaneously. What that means is that you can then tell the parent, there is a 1 in a million chance of this happening again, right? Alternatively, if one or both of the parents are carriers of a disease, then it's possible, as you say, to do a pre-implantation genetic diagnosis. You don't need to sequence the whole genome again for that. You just need to sequence the gene because you know what the cause is.
Fascinating stuff. Thank you very much, Marcel.
Thank you.
Phil Robinson is head of the self-signalling unit at CMRI, the Children's Medical Research Institute at Westmead, and he's going to talk about a new approach to cancer diagnosis and treatment options. Phil.
Thank you, Norman. These two presentations will dovetail very well. Genomics is half of the story. Proteomics is way behind, and we're trying to catch up, and we're actually trying to converge. And that's pretty much what this talk is about. So about a year ago, the Australian Cancer Research Foundation waived $10 million of equipment at the research community for a bold new vision in cancer research. We won it. And I'm going to show you the outcome of that. I'm going to start with the why in a short video, and then I'm going to show you the how we get about doing this and what all this ProCan stuff is about. So I might start with the video.
Every cancer is different. There is so much variety that what we really need to do is what the very simple concept of ProCan is all about. We need to scour the world for every new case to find, let's say, the 100 most similar cases that have ever been reported, and to find out what they've responded to so that we know what to treat the patient who is in front of us. That's the concept. It is very simple, extremely simple. The execution is very difficult, because what that means is we need to study tens of thousands of cancers from all around the world, so that when a new diagnosis of cancer is made, we already have that information in a huge international database, and we can Google what the answer is for the child or the other patient in front of us.
My youngest son, Fred, was diagnosed with cancer when he was 7 months old. We were having investigative procedures in Adelaide at 2 weeks, in Alice Springs at 4 months, in Alice Springs again at 5 months, in Adelaide again at 6 months, and we started treatment in Sydney after further diagnosing procedures when he was 7 months old. For my husband and I, it was the culmination of months of lurking doubt, the feeling that we weren't being told everything, the fear of missing something, of not being on the ball enough to ask the right questions at the right time to get the right people on the right path to give us a definitive diagnosis.
This is one of only 2 such industrialised proteomics facilities in the world, and it's the only one which is investigating cancers.
This is the place that gives parents like me hope for Fred and hope that no other child's story will have to echo ours.
It's my very great pleasure to help declare ProCan officially open. Thank you.
So ProCan launched a few weeks ago. Thank you, Minister Skinner. And I'm going to try to give you an idea of what it's all about. Our goal is to bring forward cancer treatments. And the genome will help define the cancer. The proteome is going to help accelerate the treatment decisions. And that's the kind of major point here. CMRI is particularly focused on childhood diseases. Children get cancer the same as adults, but the range and types of cancers they get are a little bit different to the ones that appear in adults, particularly leukemias, brain glioblastomas, sarcomas, things like that. So genomics is the study, as you've just heard from Marcel, of all of our genes all at once, the whole genome sequencing. So I think we all understand that at this point in time, and it's taken a long time to educate the public in what genomics means. And it's talks like Marcel's that actually inspire the public to really understand the science behind it. But very few drugs, very few treatments actually target genes. They're a small number, but not many. Proteins do the work. When you look at me, you are looking at the proteins. You're not looking at the DNA. I'm not a DNA, I'm the code. The DNA is the code inside me for the proteins. The proteomics, therefore, is the study of all of the proteins in our tissues all at once. The same way the genome is the study of the codes, proteomics is the study of the proteins that come from it. Unfortunately, you're all thinking EPO, you're thinking drugs in sports, you're thinking bodybuilding. We're not talking about illegal drugs and illegal proteins, we're talking about the normal function of all life on this earth is that genes code for cells to make proteins. Proteins fill our cells like crazy. So in yellow you have a neuron in a dish and you can see the shadow of the nucleus there in grey. But if we just look at one synapse, one fraction of a cell, a nerve terminal, and look at the structure in there, there are billions and billions of proteins in any one cell. And what the image doesn't show is they're also moving around in real time at incredible speeds. So it's crowded beyond comprehension in there. So almost all drugs, not all, almost all target proteins. They attack proteins and usually block their function. This is a particular picture of a drug our own lab has been investigating that's still an investigational drug shown bound to its target, called clathrin in this case. There are nearly 3,500, close to 4,000 clinically approved drugs from the FDA in the US that a clinician is able to choose from. It's a smorgasbord. But if they don't know which drug is the right one for Kate's son Fred, then he has to go on that chase around the world to find how to marry up the right drug with his particular personal cancer. So here's the principle. On the left you can see the genome. We all understand, I think, if you have genetic defects, it can cause a change in our tissues, a change in the cell. So the image in the middle is just intended to scare you. Again, the content of our cells is all the proteins. But a lot of other things change the proteome in a cell, not just the genome. So environments, drugs that we take, chemicals in our environment, UV light, infectious disease, inflammation, all these things rearrange the proteins in our tissues. There might be 10,000 different proteins in any one type of cell, but the next cell might have 10,000 proteins and they're slightly different. What if we could find those changes that result from disease or infection? We're focusing on cancer. So regardless of the genetics, regardless of the cause, if we can find a protein like that that's elevated, and if that protein is druggable, then we can provide a treatment option, something for the clinician to consider. And that's what we're on about. The current way cancer is diagnosed is slow and it's methodical, and genomics is really going to accelerate this in a big way, but so is proteomics, so is ProCan. The current way is to take a tumour biopsy, stain it, one antibody at a time, or actually in pairs, 2 at a time. And you can see in brown the stain of that tumour with one protein. So what it does is tells the pathologist that this is likely the cancer type, and from experience, not from evidence, from experience, this is the likely treatment that that person should receive. But our new way is something different. What if we can collect the entire proteome of that tumour all at once, not one at a time? And then if we can identify druggable targets within that as well, we're able to then rationally define what drug treatments that patient might receive. So the problem is that every cancer has a different protein pattern due to the mutations or due to any other factor in that cell. There are multiple mutations involved in cancer. So the barrier to looking at the proteins has been that there are only a small number ever produced to date scientifically, and the reliability of producing proteomes between different laboratories is not very high. In fact, it sucks. So our challenge is to collect proteomes on an industrial scale with universal and reliable outcomes. That's what we're trying to do. So to do that, we want to collect cancers from patients all over the world, starting here in Australia, where their treatment outcomes are known, and as many as possible where their genomic sequence is known, and marry these things up together. So we will analyse the proteome of 70,000 tumours of all different types in 5 to 7 years. To do this, the next few slides is how this was going to happen. So it's based on disruptive technologies and our idea of putting this into a custom industrial-like factory. So the disruptive technologies now allow us to take the smallest biopsies and liquefy them. Liquefying those samples is what's required for the study of proteomics, or proteomes. The second disruptive technology is the ability to collect proteomes on an industrial scale. This is something really quite new. And it uses instruments called mass spectrometers. And it uses a new kind of technology within those mass spectrometers that most of you are unfamiliar with, called Swath mass spectrometry. Swath has no meaning. Don't go and look up the acronym. So the final disruptive technology is one we have to develop, which is new data analytics to understand the protein maps that we're looking at. So in our laboratories, what we plan to do is have multiple instruments in a high throughput capacity in very similar way that you've just seen that Kinghorn already does for genomics. But these instruments have to work in harmony, and they've never been trained to do that before. And we need a clear workflow so we can pave the way that this system that we're trying to build, ProCan, will pave the way for clinical outcomes. So I have a floor of the Children's Medical Research Institute full of mass spectrometers, and this is the sort of thing my postdocs do. They pull the lid off, they play with the wires, they tune it and they tweak it like crazy because they're after performance. They want a few more proteins in research mode, but that's not what's going to work here. In factory mode, we have a whole set of instruments working together. And this is the world's first industrial-scale proteomics for cancer. There is one other industrial-scale proteomics that will look exclusively at blood or at plasma, and that's in Manchester. And they launched about the same time as ProCan. So the samples that we can now handle that have never been possible before are the size of the ball in a ballpoint pen, a fraction of a grain of rice. Previously for proteomics, we needed pieces the size of that grape there to do anything on this kind of scale. You can see the tiny red dot in that test tube. That's what our collaborators will send to us to analyse in ProCan, just that dot. The machines on the right allow enormous high throughput. They allow 96 of those samples to be processed in a day, and what they do is liquefy that tumour. Many of you have heard of cold pressed juice. You probably buy it in Coles or Woolies. Those are $2 million machines that apply super high pressure to liquids to destroy the bacteria and the viruses in there. So it's cold sterilisation. This uses that pressure to liquefy solid tumours in a particular environment at way less than $2 million per machine. So understanding this, we're able to buy a set of them, put them in a factory-like conditions, and get high flow-through of data for the very first time. The second of those disruptive technologies is this Swath mass spectrometer. Like the Illumina sequencers for DNA, these are $1 million machines, black boxes to you, but what they do in an hour and a half is produce a digital map of the proteins in that sample. So that map becomes part of a permanent record that is searchable. So what we are doing is putting a set of them in the same room and harnessing them so that we can get the same kind of quality data on each instrument. We do not want variation between instrument 1 and instrument 6 on day 1 and year 2. We want them working together. And that's what's already we've achieved, and it's going extremely well. The final element of ProCan is the huge computational power that's required to analyse that data. We're talking 2 gigabyte files, the size of a DVD, for each individual proteome. So that's going to add up to 2 or 3 petabytes of data by the time we are through with the next 5 years. So we're working now in the Amazon cloud environment. We have enormous parallel processing power there. And we have lots of tools that the community is providing to analyze that data. And we need to develop way more tools than that. So when we put this together in a workflow, exactly the way that Kinghorn has already achieved for genomics, well, proteomics has a particular workflow that we're trying to establish for the very first time internationally. And by working by SOPs, standard operating procedures, we expect to be able to pave the way for future diagnostic services to follow this process. But we need first to demonstrate that our data on each of those machines is highly consistent between samples and across the years. And here's our envisaged report. This is what we imagine will come out of this. And this is, in fact, the major goal of this work. So Jamie, or Kate, and her son Fred, are visiting their oncologist. A biopsy is provided to ProCan. You can see there a rapid report is available in a day or 2 from receipt of the sample. Processing time is actually under 1 day. What we'll be able to provide is a diagnosis of the tissue, the subtype B there, and the subtype. So that's a hypothetical subtype at this point on this slide. For the same way that genomics can diagnose a tumour, proteomics can do it as well, but it does it differently and doesn't rely on what the genome says. The important point are that list of response markers. Currently we're measuring 5,000 proteins in each tumour. As time goes on, that number will increase to 6, 7, and we may even achieve 8,000 proteins quantified in these digital maps that we've already collected. We don't recollect them. They're there permanent. So MGMT, for example, there is a current response marker that's measured in pathology, and if it's low, if you look at the likely response, temozolomide is the likely drug that will be used on. But if that drug is not going to work, and if the child or the adult is facing a treatment that's futile, that can be devastating. And this is why I chose Kate's story at the beginning in the video to illustrate the long journey that people take before their treatments are finalised, if there is going to be one. Now, the ones in green are really important. They're some of the list of the 3,500 to 4,000 clinically approved drug targets. If those are elevated, and there are drugs for that, we can provide that as an option list for their treating oncologist. And there are many options. In red is an experimental idea that's a research concept in the laboratory at the moment. If that is low, well, there's a new, in red at the bottom, clinically approved approach that's just come out, approved in the United States for treating that particular patient. And finally, there's research mode here, that protein X, protein Y, hundreds of other proteins in those tissues that are giving us the pattern. If they change and consistently, then we are able to, in research mode, try to identify those as new drug targets for future cancer therapies. So the bottom line there, in the bottom corner in green, is what this is about. Treatment decision tool for the clinician. And it is as personalised to Jamie as if the genome was sequenced. And when these two technologies, genomics and proteomics, are married together, we will have far more coverage of the patients that are fronting up to the doctors. So lastly, the genomics and the proteomics aligned for the first time a few months ago. So President Obama announced the Cancer Moonshot, which is a $1 billion initiative to bring forward, accelerate cancer treatments. There are many options out there, how to get them to the right patients faster. So this memorandum was signed between the Garvan and the CMRI and the United States National Cancer Institute, and was announced in Melbourne by Vice President Joe Biden. And the final outcome of ProCan also is a scientific one, and that's to make these digital maps publicly available through that Cancer Moonshot initiative so that others can investigate that data in scientific terms from a public health perspective, and lots of other ways that this can be done. This is not limited to cancer. ProCan is focused on cancer. With a scale up, and when we prove our principle is correct, this can be applied to multiple types of human disease. So we think this is going to provide Kate and her son more options for their clinician and accelerate those treatment options, but a lot faster. So this wouldn't have happened unless the Australian Cancer Research Foundation took a risk and said, Phil, what would you do with this cheque for $10 million? And it took about a minute to think of what we would do with it because we understand the technology that's available. We thank the New South Wales government who is supporting the Cancer Moonshot initiative by co-funding both the Gov and the CMRI in this joint Proteogenomics initiative to try to marry these two systems together as much as possible. And Cancer Institute New South Wales who are helping to fund some of the salaries. Thank you very much.
Okay. So once the process is done, what would the cost of a proteome be?
We are employing health economists now to work that out. The same as the $1,000 genomes, the cost of samples and consumables is only around $75 to $80. So we haven't factored in the cost of the staff and the processing yet because we're still building that capacity.
So it could be a bit less than genomics.
It'll be substantially less than genomics in the long run.
Has anyone done, just that first question, a full human proteome yet?
Yes, there are 2 papers in Nature last year on the full human proteome. And both of those studies took close to 2 years and large multinational efforts to do that.
Are you reinventing the wheel in terms of data analytics, or you can take stuff off the shelf? I mean, there's a huge capacity in the retail sector, vast amounts of information. Are you learning anything from what other people are doing? And are we going to have the data analytics in this country, or are we going to be outsourcing that overseas and losing an opportunity?
There are packages that exist now that cost multi-millions of dollars for us to use because they're based around the genomics. They have to be morphed into handling proteomic data, which is really quite different. And it's the bottleneck is how to transform the data that comes out of the machines into the language that they can understand. So we will be developing that here in Sydney through the ProCan. One
of the issues is, that's a good question. So number one is, what about retrospective testing? So you've got a biobank, you've got samples there, and you want to actually see historically what's happened to people who may have died. Can you retrospectively do a proteome on samples in a biobank? Yes, you can. So this is one of the strengths of this. You can follow the metastasis, you can follow the tumour recurrence, you can follow the reasons why the tumour might recur and chase them around the body. The issue is what ProCan will focus on in order to achieve its goals of that clinical prediction tool, we will focus on fresh frozen samples. So to use dried formalin-fixed samples, which are the more common samples, is another technology that's come along behind and is available to us in the future. I presume this is not limited to children? This is not limited to children. But at the moment that's what your focus is? No, our focus we will focus on children's tumours in order to get the samples up. But to make this work is dependent on the concept of having all tumour types included in the database. In other words, we need to create predictive power. So eventually this will become like the Cancer Genome Project. You will do it for every tumour type? Correct. Now, one of the problems and one of the false promises of genomics in cancer is the notion that you can really personalise cancer genomics, because when you do a sample, it depends on where you've taken the biopsy and the tumour, and there could be multiple mutations which you've just missed. Presumably this gets over that with proteomics because you're capturing a holistic view of the tumour. It does and it doesn't. It's a very good question, and it's one of the challenges that we face. Tumours are very heterogeneous, and a punch in one section of a tumour and the next section can be slightly different in their proteomes. We're already finding in the several thousands that we've already run that a so-called surgically dissected tumour that the clinician guarantees is pure tumour and nothing but the tumour, one of those sections is muscle and the other's tumour. So the proteome tells you that. So another question up there is about the pharmaceutical industry. So they're very good at chunking out and exploiting the situation. So you're going to find answers here, and people will develop that and keep the IP. To what extent can we control that, manipulate that? There's a parallel question which I'll ask in a moment, but there's, you do the research, New South Wales pays for this, large amounts of money go in, and then they sell drugs back to us at $100,000 a course.
So one of the elements of that is really interesting. So some of the monoclonal therapies for cancer right now are $100,000 a course. And in the case of one of the tumours I study, head and neck cancer, less than 20% of patients respond. And yet they all go on to this as first-line defence. So we will be saving millions of dollars by showing that these are futile drugs in that particular person. So this is not, we're not dependent on the pharmaceutical industry in any way, shape or form. We're not trying to foster or promote any particular industry.
So two other issues, just before we move on, because we're running out of time, is the regulatory issues here. So you're going to be actually recommending drugs off-label. So there'll be something that was approved in a randomized trial for breast cancer, and you're going to find that it's good for neuroblastoma.
Correct.
So you're going to be asking oncologists to prescribe drugs off-label.
Correct.
Safely?
Correct. So many of these will have to become their own clinical trials. That's the point. This is going to spin off into an awful lot of work to validate the sorts of approaches that we're talking about. Now, there are about 5 or 6 international consortia doing these sorts of studies right now, using the proteomics, predicting which tyrosine kinase inhibitors are likely to work based on proteomes, and then trying to get the clinical trials started. So that is absolutely what needs to happen. It's a process.
And then for the federal government, there's an issue here, is that there's going to be jurisdictional health systems that are going to be paying for these drugs, because the PBS won't, because the randomized trials haven't been done on those tumours.
Yes.
Good news for the health minister.
Yes.
I shouldn't have really asked that question, but
I didn't want to deny it.
That's right. Phil, fascinating talk. Thank you very much.
Thank you, Norman.